Okay, this is exam 3, Physics 101, fall 2015. It takes 100 meters to stop a car initially moving at 25 meters per second. The distance required to stop the same car moving at 50 meters per second under the same conditions is what? Okay, well, I know that work is equal to my change in energy. In this case, a change in kinetic energy. So the work required to stop this car is equal to 1/2 mv squared. So if my velocity is 25 meters per second, but then I double it, so I get a factor of 2 here, that means I'm going to get 4 times the kinetic energy. That means I'm going to need 4 times the distance. So whereas it was 25 meters, now it's going to be 100 meters because I'm quadrupling the kinetic energy, and so the work required to stop it will be 4 times as much. This is so it'll be 4 times the distance. This is kind of like that problem with Marie de Châtelet when she dropped the balls into the clay. When the ball had twice the speed, it took 4 times the distance. It left an impression that was 4 times the depth because it quadrupled the kinetic energy by a factor of 4. I consider this figure. A car starts at point A with a speed of 4 meters per second. And then I want to know what is the speed at point B down here. Well, I know up here it has both kinetic energy and potential energy, but down here it only has kinetic energy because since h is equal to 0, the potential energy is equal to 0. So I have 1/2 mv squared plus mgh equals 1/2 mv final squared. My masses all cancel, and I can put in my values here. I have 1/2 of 4 squared, that's 1/2 of 16, which is 8, plus 10 times 10, 10 meters per second squared times 10 meters, that's 100, equals 1/2 vf squared. So this is 108 multiplied times 2, that's 216, the square root of that. I get 14.7 or 15 meters per second. Number 2 is A. Consider the figure in the previous problem. A cart starts at point A with a speed of 4 meters per second. If the cart comes to rest at point E, what is the height at that point? Okay, so now I want to know what is the height over here. I know over here I have both kinetic and potential. Over here I only have potential energy. The kinetic energy equals 0 because V is equal to 0. It comes to a rest at that point. And now I want to know what is that height. So I say 1/2 mv squared plus mgh, this is at point A, is equal to mgh at point E. I'll put an A here. So I have the masses all cancel out, and I'm left with 1/2 of 4 squared plus 10 times 10 equals 10 times the height at point E. It's 108 divided by 10, 11 meters. So the answer is E, 11 for number 3. Okay, now consider the figure in problem 2. A cart starts at point A. Which of the following statements best describes the cart's energy at point D? Let's look at point D. Here I have potential energy and I have kinetic energy. I know that it's moving because it's still at a lower height than it was over here, so it has kinetic energy. And then obviously it's not on the ground, so it has potential energy as well. So both of them are greater than 0. D is the right answer. By what factor does the kinetic energy of a car change if its velocity is doubled? 1/2 mv squared. If I double this, I get an overall factor of 4. This is the kinetic energy. So C is the right answer for number 5. Which of these statements is or are true? Conservative forces require contact between two objects. That is not true. In fact, if you have contact, then it's not a conservative force. Field forces conserve energy. That's true, like gravity and electric forces. Friction is a conservative force. That's definitely not true. Friction does not conserve energy. And conservative forces are path dependent. They are not path dependent. In fact, they are path independent. They don't depend upon the path, the amount of work that they do. So number 2 is the right answer, A. 10 kilogram car moving at 5 meters per second, hits an initially uncompressed horizontal spring with a spring constant of 250 newtons per meter. Neglecting the mass of the spring, the maximum compression of the spring is. This just means it's a massless spring, so we won't worry about that. It's about the energy of the spring itself. We're only looking at the kinetic energy of the spring itself. We're only looking at the elastic potential energy. So here's my toy car. It's moving in this direction, and then over here I have a spring that is initially uncompressed, and then it compresses to some distance. I want to know what that is when this car runs into it. Well, initially I only have kinetic energy, and then this car is going to compress the spring, and I only have elastic potential energy. So 1/2 mv squared equals 1/2 kx squared. I can get rid of the halves, they just cancel out. And then I'm looking for h, or rather x. It's going to be mv squared over k. Square root of that, that's 10 times 25 divided by k, which is 250. Square root of that, let's see, 10 times, that's 250 over 250, square root of 1, which is 1 meter. So 7 is A. Okay, exactly the same problem. And I want to know what is the total elastic potential energy when the spring is compressed. Could have done this a couple different ways. I could have said what is the elastic potential energy? It's 1/2 kx squared. That's 1/2 of 250 newtons per meter. That's this value times 1 meter squared, and I'd get 125 or 130, and that would be the answer. Or I could say 1/2 mv squared, because I know all the energy of this car is going to go into elastic potential energy, so that would be 1/2 of 10 times 5 squared. That's also 125 joules. So E is the right answer for 8. Spring has a spring constant of 1200. You apply a force of 600 to compress it. By how much do you compress the spring? I know F is equal to kx. I'm just looking for the magnitude of the force here, so I'm going to leave off that negative we normally write. And 600 newtons equals 1200 newtons per meter times x. X is 0.5 meters. A is the right answer for 9. Machine gun is attached to a railroad flat car that rolls with negligible friction. If the railroad car has a mass of, what's that, 62,500 kilograms, 62,500 kilograms, how many bullets of mass, 0.025 kilograms, would have to be fired at 250 meters per second off the bat to give the railroad car a forward velocity of 0.5 meters per second? We had a similar problem. We have this gun. It's shooting bullets in this direction, and so it's going to have a recoil velocity in this direction. Initially, the momentum of this thing is 0 because nothing's moving. The final momentum will equal the momentum of the car plus the momentum of the bullets. Now, we don't know if it's 1 bullet or 1,000 bullets or whatever, but let's just imagine that it's 1 bullet, and then I'll show you how we figure out the number of bullets. So let's just say it's 1 bullet. So I would say that PI equals PF, 0 equals the momentum of the car, that's the mass of the car, 62,500 kilograms, times the final velocity of the car, which I want to be 0.5 meters per second. And then I have the mass of the bullets, 0.025 kilograms, times the speed of the bullets, which is 250 meters per second. Now, I also need to put in a term here for the number of bullets. Each bullet that you fire will give you a certain velocity. And I'm going to fire a whole bunch of bullets that will take me up to this velocity. So I'm going to just put an N here. Okay, and then I solve that for N. 62,500 times 0.5 divided by 0.025 and 250. I get N is equal to 5,000. Means it takes 5,000 bullets to get this car up to this half a meter per second. So number 10 is C. Okay, here's a perfectly inelastic collision. I have before and after PI equals PF. PI is going to be 2 times positive 4 plus 4 times negative 3. That's going to equal to the final, which is going to be 6 kilograms. I'll just add those two up because it's perfectly inelastic, times VF. That's 8 minus 12, negative 4, 6 VF. Negative 4, 6, that's 2/3, that's negative 0.67 meters per second. But I'm looking for the magnitude here, right? Yeah, what is the magnitude? So it's just 0.67, that's the speed. So they go in this direction at 0.67 meters per second. Open cart rolls along a frictionless track while it is raining. As it rolls, what happens to the speed of the cart as the rain collects in it? It's going to slow down. Remember, P remains constant. So this is unchanging. So if M goes up, that means B goes down. Crane drops a 0.3 kilogram steel ball into a steel plate. There's the ball speed just before impact and after impact, and at the time it's in contact with the plate. I want to know the average force. That force is delta P over delta T. That's M. The mass is 0.3 kilograms. VF is 4.2. VI is minus 4.5 meters per second. Right, it's going down initially, so that's negative, and then it comes back up again. And the time was 0.03 seconds. Oop. That's 0.3. Oh, I made a mistake here, actually. A lot of you probably made the same mistake, or hopefully not many of you. But I have VF minus VI. My VI is actually negative. So these two go away to make a positive. And so I get 0.3 times 8.7 divided by 0.03. 0.3 times 8.7, that's 2.61 divided by 0.03. I get 87 newtons. So B for 13. And a 0.1 kilogram ball is moving at 6 meters per second when it's hit by a bat, causing it to reverse direction, have a speed of 14 meters per second. What is the magnitude of the change in the momentum of the ball? Here, I'm just looking for delta P. Remember, sometimes we call this impulse, which is the change in momentum. The change in momentum is, is M times delta V, because M is remaining constant. That's VF minus VI. M is 0.1 kilograms. VF is 14 minus 6. But remember, these, it doesn't really matter how I do the signs here, but I have to think about the reverse of direction. So here, the way I'm drawing this is that initially it's traveling at -6, and then it gets hit by the bat and it's traveling at 14. And so the difference in those two is going to be 20. So that's 0.1 times 20, which is going to be 2 kilogram meters per second. B is 14. Uranium nucleus is at rest and undergoes fission and splits into two fragments, one heavy and one light. Which of these statements is true? Okay, well, I know that initially the momentum equals 0. That means that the final momentum also has to equal 0. So these two have to have equal but opposite momenta. They don't have the same velocity. The small one has the bigger velocity. The lighter one does not have more momentum. They have the same momentum but in opposite directions. And the heavier fragment doesn't have a higher velocity. It actually has a lower velocity than the light one. Force of 100 newtons acts on a 100 kilogram boulder for 2 seconds. Same force acts on a 1 kilogram stone for 2 seconds, which experiences a larger change in momentum. Well, F is delta P over delta T. So if I have a force for a certain amount of time, I'm going to have the same change in momentum. So C is the answer for 16. Which of these bodies has the largest momentum? Well, P is equal to M times V. So I'm going to just multiply these. So this would be 8mv, this would be 8mv, this would be 9mv, and this would be 6mv. So 3 is the right answer. B is 17. If the momentum of an object is tripled, if I triple the momentum, that means if it's an object that's not changing, that I've tripled the speed of the object. How does the kinetic energy change? Well, kinetic energy is 1/2 mv squared. If I triple this, that means I get 9 times the original kinetic energy. So D is 18. Which of these bodies has the largest energy? All right, so just like number 17, but here I'm looking at 1/2 mv squared. So the coefficient of v I'm going to square. So I'd do like 8 times 1 squared, that's 8. Here I would do 1 times 8 squared, that's 64. Here I would do 3 times 3 squared, that's 3 times 9 is 27. And 2 times 9 is 18. So it looks like 2 is the right answer. E is 19. 2,600 revolutions per minute is equivalent to which of the following? In 1 revolution, see I'm going to radians, it's 2 pi radians, and in 1 minute I have 60 seconds. The conversion problem here, 2,600 times 2 times pi divided by 60, 270 radians per second. So number 20 is C. Between midnight and 3 a.m., the hour hand of a clock has what displacement? Okay, well, midnight is right here. 3 a.m., when I get up in the morning, is right here. So I've gone from here over to here. That is 90 degrees, or pi over 2 radians. So I can get rid of all but those two. And then ask yourself, well, is that positive or negative? Remember, clocks, if you have a normal clock, it goes in the wrong direction, so it's negative. It goes in the negative direction, it's clockwise. The distance from the center of a Ferris wheel to the passenger seat is 12 meters, that's R. What centripetal acceleration does a passenger experience when the wheel's angular speed is 0.5 radians per second? So this is omega. I'm looking for the centripetal acceleration, I'll call it VC. That's equal to V, or excuse me, not VC. AC, which is V squared over R. But also remember that V is equal to omega R. So a couple of things that you could do here. I could just substitute this in for V, which is what I'm going to do here, and that's omega squared R. And then I have 0.5 squared times 12. Well, a half squared is a quarter times 12. A quarter of 12 is 3. So A is the right answer for 22. You could have done this a slightly different way. You could have said, well, V is equal to omega times R. So that's 0.5 times 12, which is 6. And then you would put in this 6 up here, 6 squared over R, and you'd still get 3. That'd be 36 over 12. Boy swings a 10-kilogram stone in a horizontal circle with a radius of 2 meters. The string breaks under 80 newtons of tension. What is the maximum speed? Okay, so this is the maximum centripetal force. The tension in the string acts as the centripetal force. So that is my maximum centripetal force. So I'm looking for the maximum speed. Remember, centripetal force is mv squared over r. I think I have everything here, so let's just put stuff in. I have 80 newtons equals the mass, which is 10 kilograms. Keeping 3 sig figs here. Times v squared. I'm looking for v, and r is 2 meters. So I have 160 over 10 square root. That's equal to 4 meters per second. So B is the right answer for 23. Alright, Ferris wheel has an initial angular speed, that's omega naught. It accelerates over 7 seconds, that's t. And this is alpha, my angular acceleration. I want to know the angular displacement, that's my theta. So let's sort of tidy this up. So omega naught equals 0.5 radians per second That's good. It's in radians. T is 7 seconds. Alpha is 0.04 radians per second squared. And I'm looking for theta. Well, I know that theta is omega naught t plus 1/2 alpha t squared. Omega naught is 0.5 times 7 plus 1/2 times 0.04 times 7 squared. That's 3.5 plus 4.48. This is 0.98. So D is the right answer for 24. Consider a point on a spinning wheel rotating with angular acceleration equal to 0. Which of these statements best describes the linear velocity of the point? Well, if the angular acceleration is constant, that means that omega is constant. It's not changing. So the angular velocity is not changing, but this isn't asking about the angular velocity, it's asking about the linear velocity. Now, the magnitude of the linear velocity is constant at the point on a side. However, the direction of the linear velocity is constantly changing, so C is the right answer. An object at rest begins to rotate with a constant angular acceleration. If the object rotates through the angle theta in time t, what angle did it rotate in time half t? Okay, so theta equals omega naught t, 1/2 alpha t squared, but it tells me that it's initially at rest, so I'm going to get rid of this term. So if it goes through theta in time t, what does it do in time half t? Well, it's going to go, since it's squared, it's going to go through a quarter theta. So D is the right answer there. All right.